quantum stuff now.
It is. Quantum. And then it's going to change, and no one will want to do quantum.
Well, you know, hopefully within our lifetime. Yeah. All right. So I think we can start. Just hold on for a second. So, Mirav, are you recording? All right. Yeah. So it's a pleasure to have Ian Spielman give our seminar today. Ian made some very significant contributions to the field of ultra cold atoms, including I think the first demonstration of spin orbit kind of coupling in cold atoms. Won many prizes and honors. And today he's going to tell us about coherence and decoherence in the Hofstadter lattice. Thanks, Ian, for agreeing to give a seminar.
It's a pleasure, and thanks everyone for attending, even though this be virtual. What's that?
Okay. Hi.
I think it's a mute problem. Mirav, can you?
Hi.
Okay.
All right. Yeah, so thanks again, everyone, for showing up, and thanks for the invitation. So I'll be talking about what's predominantly an experimental project, looking at what was an accidental observation that we went on to explain and understand that I'm calling coherence and decoherence in the Hofstadter lattice. And my aim is to give you first perspective about how we engineer this thing, and then to describe the phenomena that we observed, and finally lead to our understanding. So this project was performed on one of the 3 experimental apparatuses I supervise. And the champion of this, the person who did all the work, is Chiu Liang, who is currently a postdoc in my group, but in 1 year she'll be leaving for a faculty position at Purdue, and she's done wonderfully with this project. In addition, I have a project that's looking at solitons in Bose condensation with spin orbit coupling, and that's in collaboration with Justine Zwolak, who is a machine learning expert here at NIST, as well as experiments focusing on weak measurement disorder and spin orbit coupling. And these are things I won't be talking about today. Great. So what I want to lead off with is sort of a perspective about how I choose to think about cold atoms. And for this talk, I'm going to focus on cold atoms as a type of material system. And as a physicist, I find that cold atoms are really good materials in a couple of important ways. And the ways I'll focus on is that a bunch of properties that are important for understanding material systems can be both controlled and measured on pretty much every timescale that's relevant in the laboratory. So an example of this might be, for example, applying an optical lattice. Well, in a material, the lattice is there. To some extent, it can be engineered, but in cold atoms, we can turn these lattices on and off on timescales that are both adiabatic compared to the many-body evolution of the system, or diabatic. So we can access both of these sort of classic approximations you learn about in quantum mechanics class. And secondly, and equally important, the underlying Hamiltonian of these systems that describes the low-energy physics is both very well known and very simple. And what that means is this is really a prototype system where, as an experimentalist, I can work out what my Hamiltonian is. And if I need to, I can collaborate with a theory group and tell them, yeah, this is my Hamiltonian. Let's see what physicist describes. And this is by significant contrast with most condensed matter many-body systems, where you, of course, know the microscopic Hamiltonian of electrons and nucleons, but you don't know really the low-energy effective Hamiltonian that's appropriate for the physics you're trying to describe. So I would say that for understanding many-body phenomena, this is a really profound part about cold atoms as being good materials. And of course, we all know not everything good is totally good, and cold atoms are bad in many ways as well. And 2 ways which are super important is, firstly, they're really short-lived. So you prepare an ensemble of ultra-cold atoms, and this preparation process will take anywhere from 1 to 20 seconds. And once you've done it, you have a system obeying the Hamiltonian of interest. It's going to deplete away, losing atoms to vacuum and other loss processes, until on the time scale of a minute, it's going to be gone. And then you need to replenish it. And of course, if you measure it, most of the time it's a destructive quantum measurement, in the sense that it extracts all the information in the system and also expels the atoms from the trap, also requiring a reset. So every data point we do in these experiments typically comes from a new ensemble. Of course, there's exceptions, but generally that's true. And the second thing, the corollary of very simple Hamiltonians, is if you want to add any complexity to your system, you have to add that in by hand by engineering new ingredients to your system, and this inevitably leads to fairly complicated experiments. So with that said, here's a little picture of what the apparatus these kind of data are taken in looks like. This particular device starts with an atomic beam to the left, beginning with an ampule of metallic rubidium-87, which is slowed by radiation pressure, ultimately captured and evaporatively cooled, to produce Bose condensates like are pictured on the right, that are located right in the center of that vacuum system. And as a sense of physical scale, this optical table is about 2 meters long, and this Bose condensate is on the scale of about 20 micrometers from end to end. So they're fairly small things. And again, we're replenishing these and redoing it every tens of seconds or so. All right. So with that said, we can make Bose condensates. How can we engineer these things? And in quantum systems, I can organize quantum engineering into two sort of big camps, two ways of doing it. The first one I would call bottom-up engineering. Or you can think about that as micromanaging. And the idea is you enumerate a certain number of qubits you'd like to have, and these could be superconducting qubits or they could be ions, and you somehow arrange the Hamiltonian, these objects you're going to obey, individual quantum state by quantum system by quantum system. So you really engineer the network of interactions that are present in these systems from the bottom up. And this, for example, is in the pathway for digital quantum computing. You need to know what all your gates are, where all your qubits are. And that's amazingly powerful. And the largest such systems that can be individually engineered like this are on the scale perhaps of 50 ions. So they're getting pretty big. By contrast, the type of engineering we tend to do with cold atomic gases is Hamiltonian engineering. And I think this is more like as a coaching quantum system. So what we do is we build up the Hamiltonian that describes the system using well-calibrated tools, but we don't specifically tell any individual atom what it needs to do. So we might have anywhere from 1,000 to 10 million atoms in these experiments. We could apply an optical lattice. We could change how the atoms interact, or we can add gauge fields, and I'll give a little more perspective on these momentarily. And this isn't saying that each atom has to do something specific. It rather says that the many-body Hamiltonian describing the system contains these elements. And so you can see this isn't quite a top-down engineering approach, but it's very different from bottom-up engineering. And everything I'll describe today is in the category of Hamiltonian engineering. All right, so with that said, let's look at these different kinds of ingredients that you might apply. So the first one, which I will be using in the talk today, are optical lattices. And really, I think this is representative of applying potentials to the system. So if you think about the Hamiltonian describing the system, you could have a kinetic energy, and you could apply a potential. And we can apply optical potentials like optical lattices or magnetic potentials. And you can even have surface potentials if you really want to. So as many potentials we can apply, and these are naturally organized as you might think as a potential. The second term that you might naturally want to modify is interaction between atoms. And a decade and a half ago, interaction tuning using Feshbach resonances was really being understood. And the idea is that the strength of the native interaction, these nearly contact interactions we have in the system, can be tuned using a Feshbach resonance. And in the sort of picture on the right, I'm showing a transition from a molecular BEC state with basically strong attractive interactions to a degenerate Fermi gas crossing through a Feshbach resonance in a fermionic system. And this is not a tool I'll be using in this talk. The last category of tools you might think about are ones that modify not the potential energy part of the atomic Hamiltonian, but the kinetic energy part. And this is the category in which gauge fields and spin-orbit coupling can be thought about as. So here you can use different techniques, light-assisted tunneling, Raman transitions, to mess with the dispersion relation, possibly in a spin-dependent way of these systems, to really mimic all the physics altogether that you might want to study in an idealized many-body system. And I say all, and I mean that a little bit cheekily. For example, in this interaction term here, this is a local interaction. So a lot of effort right now in cold atomic and cold molecular systems is devoted to trying to create systems with longer range interactions that can have stronger propensity, for example, for becoming strongly entangled. So with that kind of introduction, this is the slide I ordinarily give about why you might want to do this. And you'll see why I say ordinarily in a second. So if you can do these things, you have new opportunities to study fundamental many-body phases of matter. And the things I'm putting in red there are the things that we have to add by hand that don't come for free in these cold atomic experiments. So for example, if you want to realize quantum Hall states of cold atoms, you need a way to have a magnetic field that imparts a Lorentz force, not just a Zeeman shift. If you might want to do quantum magnetism, you need significant spin-spin interactions. And you need something that's not zero ranged. Okay, so those are non-native things. If you want to do P-wave superconductivity, you need P-wave interactions some way or the other. If you want topological insulators, oftentimes you might want spin-orbit coupling. So those are all things that we need to find ways to add to the system. But actually, this talk is going to have a strong flavor of interferometers in it. So I'm saying this to you now so that as I go through this talk, which is going to have a whole lot to do with emulating systems and lattices, I want you to keep in mind that something about the interferometer is going to appear. So be alert for the interferometry. So in an optical context, if you want to measure a phase, you probably will build some kind of interferometer like a Mach-Zehnder interferometer. And the idea then is that you look at the intensity coming out of the two output ports that will be sensitive to the phase difference between the paths in this system. And the parallel to the Mach-Zehnder interferometer in the atomic context is a Ramsey interferometer, where the spatial direction is replaced with time, and the beam splitters are replaced with some kind of coherent pulse, usually an RF or microwave pulse. And once again, the atomic contrast in the two output ports gives a measure of the accumulated phase by whatever means quantum phase would come by during the free evolution period. And in the bottom, I plot what a typical interferometer Ramsey signal for an atomic clock might look like, showing very, very rapid oscillations. And this oscillatory signal here is marking the 2 pi accumulations of the phase present in the free evolution period. Great. All right, so here then is an outline of the physics I'd like to present to you in this talk. At the beginning, I'm going to introduce a concept which is going to be new, at least to many of you, called the idea of a synthetic dimension. And then in the second part, I'm going to begin talking about how we see quite unexpected to us coherent and decoherent phenomena in this system. And the results of this coherence and decoherence is presented in this archive paper. All right. So what we'll be doing is trying to emulate particles hopping in a two-dimensional lattice subject to large, in the sense of large Aronoff-Bohm phases per plaquette magnetic fields using the tool of synthetic dimensions. The experiments I'll be first using to sort of set this up were done here at the Joint Quantum Institute, and I guess just over 5 years ago. And in parallel, in Florence, experiments using atomic ytterbium were performed as well. And while the physical system is fairly different, one's bosonic, one's fermionic, the outcome of these experiments is quite similar. This was all motivated by theory proposal here. Okay, so here's our quantum engineering aim. Our aim is to engineer the Hamiltonian of particles hopping in a two-dimensional lattice with independent control of the hopping matrix element along the x direction and the y direction, and having the ability to install phases onto these tunneling matrix elements such that when a quantum particle undergoes a loop, it acquires an Aronoff-Bohm phase phi, which would be associated with a large perpendicular magnetic field penetrating this lattice. And in this talk, the magnitude of this is going to be of order 1/3, and we'll see that it's going to be a little bit tunable in a way that's very important. All right. Now I want to give you a heads up that there are a bunch of groups these days working on lattices with tunneling phases. And I want to give you a quick sampling of this menagerie. So for example, in a group in Munich and MIT, light-assisted tunneling has been used very effectively to create effective magnetic fields in an extended two-dimensional optical lattice. And in experiments in Hamburg and Zurich, slightly different modulation or Floquet techniques have been used to create non-uniform tunneling phases that produce, for example, staggered patterns, or in this case in Zurich, the Haldane lattice, which has no net field, but nonetheless is a topological band structure. Okay, so there's many, many different ways of doing this, and this is these days just a sampling. All right, so let's see how we do this in the laboratory. We're going to start out with a Bose-Einstein condensate of rubidium-87 atoms, And in the first part, we're going to illuminate it with a pair of counterpropagating lasers generated by a 1064 nanometer laser system. And this will make a one-dimensional optical lattice whose fundamental period is 532 nanometers. And for those experts in the audience, the depth of this lattice is 5 single photon recoils of this optical lattice. And here is a computed Wannier function for a particle sitting in this lattice. And along the 1D dimension of this lattice, atoms can hop from site to site. And the strength of the tunneling matrix element is a fraction of the single photon recoil energy. All right, so now what we've done is made a one-dimensional optical lattice. Recall that our aim is to make a 2D optical lattice. And here is where the idea of synthetic dimensions is invoked. So our atoms, in addition to having motional degrees of freedom, also have internal structure. And in the particular hyperfine manifold we're using, there are 3 MF states, hyperfine sublevels. MF equals -1, 0, and +1. And this is a typical level diagram that any atomic physicist would have been drawing since the dawn of quantum mechanics. And what we do in these experiments is invite you to think about the states comprising this spin system as sites of a lattice. So rather than drawing this diagonal system, we'll denote these as sites. Site M is +1, site M equals 0, and site M equals -1. And from the perspective of single particle quantum mechanics, this exactly is a one-dimensional lattice in which atoms can hop from site to site with a tunneling matrix element given by whatever coupling you've imparted between these spin states. In this talk, this coupling is going to come from Raman coupling or RF coupling. And here then is how this looks in the laboratory. To our one-dimensional optical lattice, we add an additional pair of laser beams that drive 2 photon Raman transitions between those 3 internal states I showed you before. And in this lattice picture, this links the 3 sites that are now available along the synthetic direction with a synthetic tunneling matrix elements that's tunable in the same units of this X tunneling from about half the X tunneling to about 5 times the X tunneling. So by linking these states, we've made a 2-dimensional lattice along one of the directions we're using the synthetic dimension concept. Okay, this seems kind of elaborate and maybe contrived. Why have we done this? Well, the point here is that because we're using Raman transitions, if you imagine a particle starting in the state here and it being transferred by the Raman transition to a state there, the 2-photon process from these 2 photons counterpropagating, the blue ones, imparts a 2-photon recoil momentum to that atom as it drives the Raman transition. And in the coordinate representation, you can think about this as writing a spatial phase upon the atomic wave function to describe the change in momentum. So the position-dependent phase, twice the single photon recoil momentum of this Raman beam times the position at where it happened. That's going to be the spatially dependent tunneling along the synthetic direction. And the sort of trick here is that atoms can only be located in specific positions along this longitudinal direction given by the sites of the optical lattice. So if I replace this X with the coordinate of these sites, which in this slide I'll call script L, you see we can bundle together all of the terms here into what looks exactly like a hopping phase. So when atoms hop, for example, from the site L up and keep inside L but change the M index, a phase is acquired which looks just like a tunneling phase. And now if you start, let's say at site L+1 and move up, you acquire a phase here of whatever phi is times L+1. You acquire no phase when you move in the lattice direction, let's say to the left. You acquire a phase of minus L times phi when you go back down, and nothing when you come here. And altogether, when you've encircled a single plaquette, you will acquire a net phase of just phi. That will be independent of where you started. So this is an explicit construction of a particle moving in a lattice described by the Landau gauge of a uniform field. And in a tight binding picture, this is the Hamiltonian actually describing the system.
What breaks the time versus symmetry here? I mean, this thing breaks time versus symmetry, but what physical field is breaking time versus symmetry?
Right. So I didn't mention, well, so there's a Zeeman shift between these levels, here and here. So in this particular case, you're quite right. There's a small perpendicular magnetic field that's Zeeman splitting those levels to give an explicit time reversal symmetry breaking in the system. There's a different way you could do it as well, which is a little bit more subtle. So we could also pick particular states of the system and drive specific transitions. and then we would focus on a subsystem of the overall hyperfine manifold. I don't have a good slide for this. The idea there is the entire system would be time reversal symmetric, but you'd be working in a subsystem that's uncoupled to the time reverse partner.
I see. I see.
But that's not what we're doing. Okay, yeah, so this
just,
so what we...
just a question. I'm a bit confused. A single atom can be in 0, -1, or +1, and then you say it hops to the second lattice side. What happens to that atom? Does it decay to the vacuum, to a ground state, or because I can't see in the single particle picture of hopping between two atoms. What is hopping actually?
So I hope this will be a satisfactory answer. I hope I give the right answer. So, and I'll show some data in a second, which may or may not help with this. So I invited you to imagine a single atom located on this site, which in physical reality corresponds to an atom in a particular point in space and in a particular spin state. Then we might imagine compelling the atom to move from this spatial site to the neighboring spatial site. I could ask what would happen if that happened, and there would be no acquired phase, and I then told the phase story. So this is a story about atoms along the longitudinal direction moving between spatial sites, and along this vertical direction, the atom's not moving anywhere in space, is having its internal spin changed. So yeah, so in this case, there's no decay going on.
Okay, I understand. You have a single atom on the whole lattice. I see. And you have its two coordinates actually, other lattice. I understand.
Yeah, so this is the picture. Now we're really going to have a Bose condensate with about 10 to the 5 atoms, but the picture, this Hamiltonian will still be the single particle Hamiltonian we've engineered for that system.
Okay, thank you.
So again, Ian, so the driving you're doing is a Raman kind of driving? There's a higher level involved somehow that?
Yeah, absolutely. So in fact, I'm going to, in the second half of this talk, I'll explicitly tell you what that level is. But correct, this is a 2-photon Raman transition that's coupling the 5s to 5p states.
Thank you.
So here is what data actually looks like. So after we've done this song and dance to the atoms, if we don't do any Raman coupling, but we do load the atoms into an optical lattice, and we suddenly, in this instantaneous sense, turn off the optical lattice and allow the atoms to expand in a time of flight, we see a very classic matter wave diffraction pattern that looks like I'm picturing on the right here. So the horizontal axis is really velocity or momentum that tells you how fast or what the momentum state of the atoms comprising the eigenstates in this lattice works. We had an extended Bose condensate loaded into this 1D lattice. This is a very standard picture. Now, in addition, we've applied a magnetic field gradient for real in a laboratory along a direction perpendicular to this lattice, or to the imaging plane, so that if the atoms had been in different spin states, the Stern-Gerlach effect would have displaced them vertically. So that's not pictured here because we had one spin state, and I'll be showing histograms showing where the atoms originated there. So if instead of using Raman coupling, like I described before, we couple these together with RF coupling, which is spatially homogeneous and carries no spatially structured phases, the associated time of flight pictures now looks like this. And what you see is independent diffraction patterns associated with atoms being in each of these 3 sites. So this is really a separable problem, and you can see the structure along X and Y is unrelated. And in fact, if we histogram the structure along the vertical direction, we get at a discretized version of the expected single particle in a box wave function. Okay, so we've recovered that, nice. So now I want to sort of give you an idea about what to think about when we start using Raman transitions rather than RF coupling. So a key thing is that there's going to be a distinction between where the states are in the system. There's a coupling, let's say edge, this is for a quasi-classical picture, of course, but sort of skipping edge states on the top and the bottom and localized cyclotron orbits in the bulk. And a key point is that the cyclotron radius here, in fact, can be smaller than the extent of the system. And in the quantum sense, this will take you away from the single particle eigenstates I showed you before. And here's, and if you do a continuum quantum mechanical version, again, looking in the lowest Landau level, we see that this too supports edge states associated with the Fermi energy hitting points at the edge of this box. So here we go, here's some more data. So this is with RF coupling. See the particle in a box state. If we do the exact same experiment using Raman coupling and focus in a state prepared in the center, we get this. And I want to draw your attention to two features. The first feature is that the vertical and horizontal directions are now coupled. In the vertical direction, we see that as you move upwards, the dots you image are displaced. And this can very loosely be thought about as the momentum acquired as a particle experiences a Lorentz force as it tunneled upward. And in fact, if you do the calculation, that will in fact give the right answer. Secondly, you'll notice the distribution, the spread of momenta is much narrower than it was before. And this is because at this particular field, the cyclotron orbital size is smaller than 3 sites, meaning we've narrowed the wave packet to give this. Okay, cool.
Are you saying that the atoms don't, you know, that we see at the, say, these corners of the hexagon, the particles are not sitting at the minimum of the lattice potential? So should I interpret it like this? Or is it the fact that the way you're imaging this, I mean, I have to, yeah, the translation between momentum and position is different.
That's right. So the first thing you said is correct, that if you look at the wave function associated with the eigenstate that is most close to the center of this, so sort of in this condensed matter language, thinking the continuum case, there would be Gaussian-like wave function in the center of the system.
Mm-hmm.
And this eigenstate is the lattice analog of that one. And a little bit of the amplitude of that eigenstate leaks over into this neighboring vertical site. And indeed, the momentum at which that amplitude sits is not at the minimum of the 1D dispersion relation. It's exactly displaced by this amount. So there's no trickery in this image.
I see. So it's not the position, it doesn't sit on the lattice side, it's just the momentum. You have an extra momentum.
Exactly.
I see.
Yeah. And then if I finish this story, this system also supports edge eigenstates. So for example, on the bottom side, if we adiabatically load an edge state down there, we can see that it's predominantly located in the edge, and a little bit of its amplitude leaks upwards. And here is the histogram of where it's located, and vice versa if you locate on the opposite edge state. All right, so that's all good. We can engineer eigenstates. The second to last thing I want to show you in the sort of primer on synthetic dimensions is we can engineer dynamics as well. So we can, for example, prepare atoms on the bottom of the system and suddenly allow the vertical tunneling to take place. This means we abruptly turn on the Raman lasers to a system that was already loaded in the lattice. And if we do that, we can see skipping orbits as the atoms bounce down the side of the system, both whether we loaded them on the bottom, as is pictured by the cartoon, or as we loaded them on the top, as up there. So we can see these beautiful skipping orbits, and data of this same type was also observed in the Florence group. So we can do statics and dynamics. So in doing this experiment, we also took data like this. This was sort of calibration data, really. It did make its way into the paper, but the idea is that you prepare atoms in the middle site and then suddenly turn on the synthetic hopping. And now the sort of, if you will, the 0-point pressure of this gas pushes atoms up and down, initially occupying states on the top and bottom, before after some amount of time, the wave packet on the top moves to the right, the wave packet on the bottom moves to the left, and they recombine. And we see nice Rabi oscillations in the laboratory. So this was, when we did this, it was more confirming our model than anything else. And that theme will appear in a couple of slides. All right, so keep this in mind as well. So I've asked you to keep this data in mind, and I've asked you to keep interferometers in your mind.
And why are we limited to only 3 sites on the synthetic dimensions?
So these experiments are being performed in the F=1 hyperfine manifold of rubidium-87, which has 3 sites of 3 spin states available.
Mm.
We also have a result out where we worked in the F=2 manifold of rubidium to do a 5-site wide strip.
Mm-hmm.
And in the rubidium system, you could have as many as 8 sites if you coupled all of these states together.
Also, do you have a strong confining potential in the spatial direction, or the fact they're just very, I mean, it seems like the atoms are not dispersing much in the spatial direction.
Yeah, so I think the appropriate answer to that is that we have a relatively weak confinement along the longitudinal direction. Mm-hmm. So that on the scale of individual lattice sites where this motion is taking place, you can the displacement compared to the system size is very small. So in some sense, this cartoon is misleading. It's not 5 sites in extent, it's more like 40.
But the fact that we're seeing the atoms localized on a certain site is I mean, in these,
So-
that's those momentum pictures, I see.
That's right. And so
I see. Okay.
we start with the atoms localized very strongly in this vertical direction, as is pictured here.
I see.
So we have single site imaging along the vertical
Yeah.
direction using the Gerlach trick,
Right.
and then momentum imaging along the longitudinal direction.
Okay. Thank you.
All right, so in the second part of the talk, the new results, what we have done is taken this 3-site wide strip and roll it into a tube. And this now is the work of Chiu. So when we began this experiment, what we were aiming to do was realize the Laughlin charge pump. So Laughlin's idea, which is completely ridiculous in the material science realm or engineering quantum wells, is to make a quantum Hall loop like this, 2D electron gas, and then thread a magnetic field through it in addition to the perpendicular magnetic field. And what he pointed out was that every time you thread a flux quanta through the system, one electron will look like it has moved from one site to the other, when in fact every electron will have moved by one site in a lattice picture.
But you can do that for Brino geometry. It's not that, it's that an annulus is the same, so it's not that ridiculous.
Yeah.
Yeah.
So what was I going to say with that? Oh yeah. So if you haven't read this paper, it's worth a read. It's 2 pages long. It has 4 references, only of which one is to theory. So it's quite a little note. So what we were aiming to do is replace that difficult to realize ring with a engineered quantum tube like this, and then by engineering phases in a time-dependent way to emulate the behavior of threading a flux longitudinally down this system. So that was our goal in the laboratory. And the way we were going to do this, we needed to do this is with this synthetic dimension trick to couple 3 states together in a cyclical manner here. And the sort of way we wanted to do this is laid out by the proposals down there from my group. And I want to point out that using slight variations on this technique, 2 other groups that I'm citing down here have in one way or the other also realized something like a tube, well, a tube geometry, not something like it, a tube geometry. Okay, so if you're interested, those references there. And now we come to atomic structure.
How do you couple spin states that have, angular momentum difference of 2? You need to couple them directly, so.
Yeah, so if I don't answer this with all of these pictures of atomic structure, ask again, okay?
Okay.
So one way, the most naive way you might think of doing this is using the same kind of Raman coupling we were already using. So imagine 2 counterpropagating Raman beams, Raman spatial modes with different frequencies on them. So one drives the transition from -1 to 0. Another pair, or the same pair, drives the transition from 0 to +1. And then a different pair drives the transition from 1 to -1, all arranged so they give the recoil kick in the same direction. So that would be scheme number 1. And our lasers are tuned to drive transitions from 5s, had the intermediate state between 5p, and then back down to 5s. That's our 2-photon Raman transition. And what you will discover is that if you want to drive a MF by 2 changing transition, so to use both units of angular momentum available in your photons, you have to be super close to resonance to either this D2 or D1 line there, and that has a prohibitively large amount of spontaneous emission. So this naive implementation in terms of a tripod scheme just is not going to work. So we will rule that out. A second scheme, which in fact has been used in one of the ring papers I cited to, is to select 2 states in the ground hyperfine manifold and 1 state in the excited hyperfine manifold, both of which are in the electronic ground state of the atom. So now we drive a transition from there to there, now from 0 to F equals 2, MF equals -1, and finally from F equals 2, MF equals -1 back down to 1 -1. This now involves MF changes by 0 or 1 and gets rid of that super close to resonance requirement. And this can be operated reasonably far from resonance to reduce spontaneous emission. So if you work in the laboratory, though, you'll come to the unfortunate realization that there are spin exchange collisions between atoms in F equals 2 and F equals 1, that on this particular pair, angular momentum allows that transition to a de-excited atom from F equals 2 to F equals 1, thus liberating a bunch of kinetic energy and removing atoms from our system. And this gives typical lifetimes of sub-100 milliseconds. So if the goal is to do mini-body physics, that's our sort of the aim with this, we would rule out that scheme as well. Boom, it's gone. So lastly, something I haven't mentioned, which is a purely technical point, is that all of these transitions are first order sensitive to magnetic field. And as we try to do more and more careful experiments, this first order sensitivity is increasingly unacceptable. So we'd also like to work on a pair of clock states. So for example, the states in black there. And it may not be lost upon you that there are 2 such clock states, not 3, so we can't even do a 2-site strip. So we rule that out as well. All right. So what we've done here is rule out every possible combination of states in the entire rubidium level structure. So this might be a sign that you should give up. But what we did instead is talk to our quantum information colleagues who told us about something called continuous dynamical decoupling. And when you read a quantum information paper, this seems like almost magical. But in fact, it's not. If you're an atomic physicist, it's a relabeling or renaming of something we've known about forever, which are address states. So the idea here of this continuous dynamical decoupling is to apply a reasonably strong oscillating external field, in this case an RF field, that will couple together the 3 states of this F equals 1 manifold. So the red arrows are meant to mark the RF photon energy. And in the address state picture, this gives the states I'm sketching on the right. And what you should first notice is that there are 3 of them. Secondly, you should notice that at resonance, each one of them has 0 derivative. That is to say, they're first order insensitive to magnetic field. And thirdly, by the way we've constructed it, the superposition of these address states allows 2 photon-Raman transitions to be driven between all 3 of them using far from resonance beams. So it's highly field insensitive. We've measured it to be, in fact, 4 orders of magnitude less sensitive to magnetic fields than the bare states. Secondly, here's a plot of the measured matrix elements showing that indeed we can drive transitions between all 3 of these states, which we are going to call the X, Y, and Z states. All right, so sweet, we now have a scheme. So we're going to turn back to our goal in the laboratory. What we'll do now is similar to before. We have a Bose condensate, an optical lattice, a pair of counter-propagating Raman beams. Now in this case, one of these Raman beams has 1 frequency on it, and the other Raman beam has 3 frequencies on it, so as we can resonantly address each of the 3 Raman transitions we would like to address. In doing so, we now map the 1D lattice again to a longitudinal direction and the 3 states to the cylindrical direction here. So we've taken our strip and we've rolled it up into a tube. One thing I want to call your attention to, this is purely laboratory stuff, but full disclosure here. The first experiment I described used a 1064 nanometer laser. We switched that out to a 532 nanometer laser, thereby making the spatial periodicity of this true 1D lattice half as big as it had been before. All right. So whenever, we did the synthetic dimension experiment 5 years ago, that was with an old lab and an old team. So we actually did this project on a different apparatus. So we have a new lab, new team, and even a new preferred color scheme. And whenever you enter into an environment with this many differences, you want to do your calibration experiment first. So we did exactly the same experiment we did before. We loaded the atoms into the central state. We did not have periodic boundary conditions, and this is super convenient with this setup. If we want a hardwall boundary condition, we simply don't turn on one of the sidebands on the one Raman beam with 3 tones in it. We just have 2 tones in it, and therefore make a strip. So we set up this experiment. So on the top is the data I showed before, and the bottom is the new data. And what you see, and we're only plotting the top state. So you can see the evolution time scale is different. So this is going to maybe nearly 2 milliseconds. This one was 4. That has to do with changing the periodicity of the lattice. But we're seeing qualitatively the same structure, decaying oscillations. Okay. However, this is a picture I pulled out of the lab book for this talk. As soon as we made periodic boundary conditions, we closed the link from there to there. This is what we saw in the laboratory. So in this graph, every point is a single data point, no averaging. Here, every point is a single data point, and the bars are plotted on there to represent the standard deviation. So as soon as we closed this loop, the data became incredibly noisy. So usually when data becomes incredibly noisy in a laboratory, you've made a mistake. So we phase locked all our lasers, we stabilized everything, and this kept on happening. So this is the central puzzle. We're trying to do a Laughlin pump, and instead we stumble across a lot of noise. And now I want to return to the second thing I asked you to think about at the beginning, which is an interferometer. And I want you to really think about an Aronoff-Bohm interferometer in this case. So in that case, in the Aronoff-Bohm picture, you have an electron beam, you have a solenoid, and the picture is that if you look where the electrons recombine, you'll see a standing wave interference pattern whose phase is proportional to the magnetic field penetrating this loop. Okay. It looks like we've engineered exactly that scenario in the laboratory. We have a loop. We have the capability of inserting a longitudinal flux down that loop. So ought not the atoms, as they encircle this loop, which we start in the pink side and release them, ought not they interfere with one another in a way that might be sensitive to this longitudinal flux? Okay, so that is now a question. Let's think about that. And the answer to that question experimentally is sort of. So here now is a reduced data, the type I showed before. And now I want to call your attention to another detail which I had been glossing over. In the previous data I showed you, the longitudinal flux was, this is the first half of the talk data, the longitudinal flux was actually 1 1/3. In doubling the lattice period, we've changed this flux to be close to 2/3. Now here it was approximately 1.32, was definitely not 1.33. One of the things we did in this new experiment, because we were aiming to the Laughlin charge pump, we knew we were aiming to sit exactly at 2/3 flux per plaquette for the reason that there you have 3 topological bands and you would expect to see a charge pump behavior. Indeed, if we now perform this simple time evolution experiment of preparing the atoms in state 1 and releasing them at exactly 2/3 flux per plaquette, the data is incredibly noisy. However, if you move away by a really tiny amount, in this case by tuning the wavelength of our Raman laser, the noise vanishes. And what I'm plotting here, along with the data, is a numerical model of the full system, showing both the average evolution as the gray curve and the standard deviation of that evolution, assuming this longitudinal phase is being drawn by a uniformly random distribution. And you can see this agrees spectacularly well with the data in every regime. And the bottom graph is a plot of the residuals.
What is again the reason for these fluctuations? There are fluctuations in phi, or?
Yeah, so first, to address that question, in this system we have an additional degree of freedom we didn't have before, which is a longitudinal flux I'm calling phi longitude. And the aim of the experiment had been to linearly ramp that in time to see the Laughlin charge pump phenomena. And what this data is telling you is that there is an uncontrolled variable in the laboratory that no matter how hard we tried to fix it, we couldn't find it, that leads to this phase being randomized from repetition to repetition of the experiment. Yeah. And what this picture is showing you is that the data is fully consistent with that, and we only have this type of interferometric sensitivity at 2/3 flux per plaquette, not a nearby rational number. And this graph is showing one more conclusion, which is that the average evolution at 2/3 is indistinguishable from the evolution near 2/3. So the gray curve here is the difference between the models, and the red dots are the difference between the average at 2/3 and the average at not quite 2/3. All right, so we have a couple things to explain. Oh yeah, so now we go look at the numerical model. And we see that 2/3 isn't special. What I'm plotting here is the amount of noise we'd expect to see, the normalized variance. And this is a completely model as a function of transverse flux. And what you see is excess noise at simple rational fractions. Okay, and as the rational fraction becomes, quote, less simple, involving larger integers, the amount of noise decreases. Okay, so if we think about our system for a second as being a kind of 1D lattice, when it's a 1D crystal, at a rational flux, it's a 1D crystal. And at a irrational flux, let's say the golden mean, it in fact is a 1D quasi-crystal. So what's going on here? All right, so in order to explain this and give a picture of what's going on, I need to have a one-page primer on band structure. So all the band structure you really need to know is if we create a one-dimensional optical lattice, the lowest block band of this optical lattice here is described by a cosinusoidal band structure that is minimum at the center of the Brouillon zone and reaches its maximum at the edge of the Brouillon zone. And our lattice depth is sufficiently large that the excited bands up here play no role in the physics. So we're going to forget about these bands and focus only on this lowest band here. And this understanding of what this band structure for motion in the lattice along the x direction is sufficient to draw a sort of pictorial intuitive representation of what's going on. So first, let's think about this picture not in real space, but in momentum space. So if you were started at 0 quasi-momentum or 0 crystal momentum along the x direction, and this is our initial state of a Bose condensate, this sort of gray blob here is describing the width of the initial wave packet. We ask what happens after the system undergoes 3 Raman transitions to make it back to the same state. Remember, this is a loop. Well, every time it undergoes a Raman transition, the crystal momentum changes by twice the single photon recoil of the Raman lasers, which is not the same as single photon recoil of the optical lattice lasers. So for example, it might move to this blue position here after 1 transition. After 2 transitions, it might move to this sort of greenish position. Now keep in mind that the states are 2-pi periodic. In this band structure, that's exactly the same as being in that state. Over here, and the final transition will move you once again back to the original state with a slightly different momentum if these frequencies are not commensurate. And this is what data looks like that sort of pictorially represents this conclusion. We're starting where this blob is. As we move to the blue state, we're displaced to the left, as is pictured there. As we move to the green state, we move further to the left, which is there, and that's the same as there. And finally, when you come back, you end up in the pink state again. So the nature of the interference in this is that if in momentum state, the incommensurability of these 2 periodicities of lattices is large enough that the final wave packet depicted by the displaced gray wave packet does not overlap with the initial one, you no longer have closed a loop in the sense of an interferometer, and we expect to have no phase sensitivity. Okay, so that's the intuitive picture. And the sort of way to understand this a bit more carefully is to think about, well, here's our full reduced model describing the system. This lowercase phi is the tuning parameter that controls this longitudinal flux. And if we look at this, we can understand the system as being decomposed in the long direction into individual 1D lattice models. And we can do this by taking a Fourier transform of the system along just one direction, in this case, the long direction. And if you do this Fourier transform, to your delight and amazement, you will discover that the system converts into a decoupled set of 1D lattice models, the Aubry-André model, in fact. So the Aubry-André model is a model describing the motion of particles in a potentially incommensurate 1D lattice potential, with hopping along hopping along one direction, accompanied by the presence of a lattice potential along the other direction. Now, in this mapping I've just made, what I've done is convert the degrees of freedom describing the system are sites, but these sites in fact represent momentum states. So in this longitudinal transform, I'm looking at k states along the long direction and spin states along the short direction. And I associate these sites of, quote, the Aubry-André model, and I'll show you viscerally where it comes from in the next slide, are being tunnel coupled by the Raman coupling. And they acquire a sinusoidal potential they move in from the dispersion relation of the lattice. So pictorially, rather than that sort of annoying mathematical part, here's what's going on. If I label that initial black dot as a state, that might be the n equals 1 state there. It has an energy from the dispersion relation of -2t. If I then undergo a Raman transition to another state here, a different momentum state and a different spin state, its energy is different. It's at some other value crystal momentum. And finally, if I undergo another Raman transition, I end up here in a different state with yet a different energy. When I come back, I'm in a nearby state here with a different energy. And the key point is that each of these energies result from sampling different points on this cosinusoidal dispersion relation that, with respect to the lattice of these connected points, gives rise to an Aubrey-Andre model. So that's the Aubrey-Andre model picture there. And again, if we're to commit a rational fraction, at some point as you wrap around, going to every different final point in this black curve, you'll finally arrive back in the point you started with, closing a loop, making an Aubrey-Andre loop in this sort of hybrid synthetic dimension momentum space lattice. And in this picture, we can understand the origin of coherence and decoherence by whether or not initial states have the opportunity to interfere with one another. So in this example, I've picked an irrational fraction that is nonetheless quite close to the original rational fraction of 2/3. And what I'm plotting is wave function amplitude with the gray bars, resulting in sampling this initially finite wave packet resulting from our system's finite size. And you can see there are 3 nearby states in this lattice with significant amplitude in them. And because it's incommensurate somewhere else very far away in this lattice direction, you'll have 3 more states and so on off to plus minus infinity. The idea here is that if the mismatch between these momenta is large enough such that this first black dot is appreciably outside the initial wave packet, then this state here, when it evolves, will have nothing to interfere with. Whereas if, as pictured here, there's significant amplitude in the neighboring states, just by tunneling 3 sites in this Aubrey-Andre picture, there can be significant interference between these initial states. And here is the sort of data version of this. The left case is the ribbon case. This is the case where you don't have periodic boundary conditions. And the Aubrey-Andre picture sort of corresponds to chopping the Aubrey-Andre lattice every 3rd site, in which case there's obviously never any interference between that state and that state. Secondly, if you're at exactly 2/3 flux per plaquette, you can see that just by hopping 3 sites, one can interfere. And in time of flight, we see only 3 momentum states occupied. And by contrast, if we move away just a little bit, we can see that as atoms hop from site to site, many, many momentum states appear to be occupied, there and there. And when we're very, very far away, we return to a case where it looks like almost no tunneling takes place at all. So finally, this is giving us some picture of what's going on. And if we look very carefully at the numerical picture of this, we'll see that indeed in the ribbon case, we expect no noise. So the top here is the numerics, the data, and the bottom is numerics. If we're exactly at resonance, meaning a commensurate rational fraction, we see very noisy data. And if we plot the individual trajectories produced by our numerics, we see this even reproduces the caustic-like behavior present in the data. And as we move slowly away from this rational fraction, we see the noise decreases both in the data and the numerics, and far away the noise vanishes. This allows us...
The noise in the numerics is introduced in what parameter?
So each numerical trajectory is run with a different value of the longitudinal flux. So we're simulating over an ensemble from a longitudinal flux running from 0 to 2 pi. And I think I ran 128 trajectories to plot that. So altogether, the data can be summarized by this graph. The vertical axis is a measure of the variance of the data, and the horizontal axis is the transverse flux. The open gray data points are the amount of noise observed with the open boundary condition case, and the solid data points is the amount of noise measured in the periodic boundary condition case. And the black curve sitting on top of it is the prediction of our model, the numerical model with no free parameters of any kind. So we're highly confident now we've worked out the origin of the phenomena we were looking at. And I see that my time is short, so I want to point out one more observation that I mentioned at the beginning, and I will not go through a thorough explanation of it. So this observation is that if you look at the average time dependence, so I'm going to focus on the graph on the right here, as a function of the transverse flux, rather than seeing a sharp peak exactly at 0 deviation from 2/3, rather we see a time dependence which is largely independent of the transverse flux. And this is the average time dependence. And then if we look at the numerical model, that's what we expect as well. So there's an additional phenomena here, which is that even at the noisy position, the place where we have a high sensitivity to the longitudinal flux, the average behavior is completely unstructured. And the physical origin of that in the Aubrey-Andre picture is that when you average over the ensemble, the cross terms from the different points in momentum space interfering from one another average out to 0. And you end up with the average behavior of the large amplitude points averaged with the nearby small ones. However, because the structure in this sort of energy landscape here becomes increasingly weak as you approach 2/3 flux per plaquette. In fact, each one of these sources that is not interfering with this neighboring force in the ensemble average is in fact having essentially the same time dependence. And that goes to explain the independence, the flux independence of the ensemble averaged time dependence. So in the bigger picture, this kind of experiment sort of bridges together two ideas in controlling coherence in atomic quantum systems. So in the first sense, we've constructed what's kind of like a new kind of decoherence-free subspace. In that sense, we simply change a flux to a very irrational fraction, very close to a rational fraction, and the sensitivity of our system to the external variable, which is the longitudinal flux, vanishes. And secondly, we've done this using an Aubrey-Andre model in an irrational fraction, which is sort of a paradigm model for almost disordered system, for a quasi-disordered system. So much like in pictures in collisional narrowing or environmental assisted tunneling, which both represent true kinds of disorder, we can reestablish coherence in the time evolution of a quantum system by introducing something which is a lot like disorder. And with that, I'd like to conclude with some questions we have about this. So questions are, we performed this at a very specific value of the ratio between the tunneling parameters in the Aubrey-Andre model. And that ratio is what was easiest in the experiment to do. So a really neat question is, well, how does this relate to the metal insulator transition in the Aubrey-Andre, which is of course not present in the true model of disorder in 1D. And another question, which we've looked at numerically, is the degree of protection does this kind of disordered deep-free subspace behavior give you to time-dependent noise? And in fact, we can show that it also protects against time-dependent noise, but we don't utility of that. So with that, I'd like to end and sort of advertise real briefly a bunch of other fun stuff my group is doing to encourage you to have a look at papers about Rauschba spin-orbit coupling or stripes or analogs to pair production or so forth. And then I'll return back to questions. So thank you very much.
Thank you, Ian. Let's see if there's any questions.
I have a question. So would it be interesting to, I mean, now that you have these three transitions, would it be interesting to not give them at once, but modulate them such that you can actually do like chiral, choose the direction and break the symmetry, do you see my point?
Yeah, I see your point. So I can say a couple things about this. I think that question isn't as, yeah, I think it's really neat first. Let me answer that part. So it's actually not as obvious as you might think, the time reversal symmetry breaking in that case, particularly with 3 sites. And the reason being that the evolution, let's say you do an experiment where you start in site 1 and then have a pi pulse to site 2, and then a pi pulse to site 3, and a pi pulse back to site 1. You would be believing, therefore, that there's a chirality that maybe gives you counterclockwise behavior. I would ask you, what happens if you started at site 2? Well, the first pi pulse would move you to site 1. The second pi pulse wouldn't do anything, and the third pi pulse would move you to site 3. So in fact, that state moves in the opposite direction, half as fast, well, 2/3 as fast. And the same is true, the same sense of thing is true if you start in the other state, that start in 3 state, the first pulse does nothing, the second pulse moves to the opposite direction. and the third pulse does nothing. So this actually has to do with the earlier question about time reversal symmetry breaking or not in this system. So there, if you confine yourself to the dynamical subspace associated with starting in site 1, you indeed have chirality. But the aggregate, an arbitrary initial state, does not exhibit chirality in that case.
I mean,
So
you could.
this is really, and we're doing an experiment right now related to this in a double-well optical lattice, where you do exactly such pi pulses, leading to hopping either along the left or right direction as a way to build essentially edge state kind of things, linearly dispersive states in a 1D model. But they always come in pairs.
I mean, yeah, you could separate the edge states. You know, if you have a 2D system and you could do pi pulses in both the x and y directions, then you could end up with chiral edge states which are separated.
Yeah, I'm familiar with this sort of this plaquette picture of creating edge states.
Other questions?
Great talk, but I'd like to go a bit slowly on how you instill these phase differences between two states. I didn't get that. I mean, with the Raman field, you managed to put exactly a flux phi between two states and then another phi between two other states. How do you do that?
Okay, so I hope I'm going to answer the question you're asking. This sounds, and we'll see if this goes to where you want. In fact, I think the slide that's most useful for this, I have an equation here. Okay, so there's two ingredients I think I'd like to point out to you here. So the first, someone has, microphone on. So the first one is this picture that if you start in MF equals 0 in an extended state, like a Bose condensate, so many lattice sites in extent in atomic state, and you undergo a Raman transition that moves such an extended atom up to this vertical collection of states. The way you describe that process in the coordinate representation is to both change the spin and write the spatial phase onto the system. Okay, and when you discretize into the coordinates of the lattice, the phase that gets written onto the system is simply the ratio of the optical wavelength, or if you want, the ratio of the wave vectors of the light. And with the lattice that this first experiment was done with, that ratio worked out to be 1.32.
So the two lasers are completely incoherent from one another, but the only thing you know is the ratio of lambdas, and that's enough to give you this phase, you say?
Yeah, and you asked you stated something which could be framed as a question, right? So the lattice laser here has no relative coherence with this Raman laser here, except that the wavelengths are known with high accuracy. So the way we tune this flux, that's the transverse flux in this 2D plane, out of this 2D plane, is by shifting the wavelength of one of the two lasers. And the one we select to shift is the Raman laser. And the reason for that in the laboratory is this is generated by a tunable titanium sapphire laser. So it's a tunable one.
But what will determine the sign of this? I mean, this is always a positive number. And it looks like you could put both a positive or a negative phase. How do you tune it to be the sign you want?
I have a slide for that.
Okay.
So I think it is, it's one of these hidden ones here. Yeah, so let me just go from this view. So here's the data first before I explain how we did it. So everything here is a sort of plus 2/3 or equivalently plus 1/3. And what I want you to sort of notice is that the dots always sort of look like they shift to the right as you move upwards. If we flip the sign of the field, the signature to that happened is the brightest dots now move to the left. So if I sort of go back and forth, you can see that pattern flipping and flopping. Okay, so first that's the data. Now, how did we accomplish that task, which is actually a question? So the way we're doing this is driving 2 photon Raman transitions between these two atomic states. Let me move this right here and play again. Okay, so we're driving Raman transitions between these three states. And we control which way the momentum recoil is. So again, let's say you start at MF equals 0. You absorb a photon from beam one, the lower energy of the two beams, and you're stimulated to emit into the higher energy of the two beams if you want to go to MF equals +1. So to this picture then, one of these beams, let's say this one here, has a slightly higher frequency than this beam. And these two beams do have a well-defined phase relationship with one another. So to flip the field, I select which of these two beams has a slightly higher frequency.
I see. Okay, so that's putting in a phase between two states. And now between three states, how do you generalize that?
So in this picture, so for this experiment here, what we're working in the regime where the linear is the Zeeman shift is extremely linear, so there's no significant quadratic contribution. So the transition between this state and that state, and this state and the next one is driven exactly by the same pairs of lasers. So I get the same kick from here to here as from there to there, and I write the same phase. So for this experiment, it came for free. By contrast, for let's say, maybe it's most clear with this picture. For the experiment we did next, where we used these dynamically decoupled states for the basis states, one of the Raman beams had one frequency on it, and the other one had three frequencies on it. So each one of these transitions, Z to X, X to Y, and Y to Z, were driven by separate Raman transitions. So in exactly the same sense, we control the frequency of each of those three sidebands comprising one of the three beams with respect to the frequency of the one beam going the opposite direction. So we completely have the capability, for example, by building a lattice where you have a positive flux coming out of two of the sides and a negative flux in the third one.
I see. Okay, thank you.
Any more questions? Yeah, and I have maybe, I don't know, maybe it's a silly question, but I mean, which regime do you consider more coherent? The one where, you know, the flux is, you know, an integer fraction, 1/3, and then you actually see interference, or but a lot of noise then, right? I mean, I hope I understood correctly.
Yeah, so
the other regime, yeah.
Actually, it's a really great question if we want to define what we mean by coherence, right? So what I mean, I'll be quantitative by what I mean first. So if I construct an ensemble average density operator describing this system, I'm focusing on those coherences in that density operator that are giving rise to the variability in these data. So in this case, the case at 2/3 is the incoherent case. I've lost the coherence that allowed to have the uniform time evolution here. But this is not a simple 2x2 system. So even though I've recovered a nice unitary looking time evolution here, that is specific to the variable I'm looking at.
Right.
When this random flux is being drawn, if we hadn't looked at this variable, we looked at individual site occupation, for example, you'd find that that would still be fluctuating in many cases. So it has very much to do with which coherence in the density operator you're looking at. And this experiment really is one of luck, where we were trying to do one thing and we had something which to me is far more interesting happened instead. And we just happened to have an observable that revealed it.
I see. And these fluctuations again in this flux are arising from what?
Okay, right. So that is a question we don't know the answer to. So there are many things, in fact, starting with the previous question. So the 1064 nanometer, well, in this experiment, the 532 nanometer laser making the optical lattice, if that lattice moves with respect to the Raman fields, in fact, it introduces this phase, but we phase lock those. So that should be good. If any of the relative phases between the different Raman fields fluctuate, that's a problem. We verified that's not the case. Using this dynamical decoupling trick we used, it turns out that if the phase of the RF oscillator varies with respect to the Raman sidebands, that causes fluctuations. We locked those as well. So it's probably like a mirror moving somewhere in the lab, to be honest with you. And we didn't find it. So what we did to make sure that we were in this regime is that we deliberately randomized these phases from shot to shot to make absolutely sure that we were drawing in the experiment from a uniform random ensemble.
I see.
And all the story is really a single particle story, as you said? I mean, or is there any remaining effect to the effect you're using a BC and not a single particle rate?
I'll just use this picture. The BEC, okay, so first, in this particular experiment, the many-body properties of the system have two impacts. One of them is bad, and that is you may notice that this thing is sort of decaying away with time. The oscillations are getting smaller at longer time. And that is an effect that's coming from collisional interactions between the atoms during this unitary evolution, scattering them to different momentum states. So that's a bad thing. The interactions are also governing the system size. And I didn't mention it in this graph, the size of these peaks is related to the system size. The smaller the system size, the broader the peaks, because the momentum space wave packets become larger. So those are the two primary effects of interactions in this experiment. Here, the complexity is coming from the fact that you have, when you go to incommensurate rational fractions, the Hilbert space is large in the sense of having to include all the spatial degrees of freedom. So it's not many-body large, but it's a lot larger than you're used to in an optical lattice experiment. So there's sort of an intermediate level of complexity here between real many-body physics and conventional single particle physics. The physics we are really interested in, and I have one remaining apparatus that would be working in this kind of direction, is going into real 1D systems. So I didn't describe at all what happened along the laboratory perpendicular directions. Here they're just inert. If we tightly confine the system into either tubes or use a Laguerre-Gauss beam to make an individual 1D trap, we get into the regime where we get quite a lot of interesting many-body physics, both in the periodic and open boundary condition case. So that's a direction I wish to go. And I had really honestly thought the Laughlin charge pump was going to be easier than that.
Are there any other questions? If I may, I have another question about this CCD. Does it introduce a lot of extra heating, or?
No. In fact, if we just do the paper. This 2008 PRA is where we describe this technique, and these measurements came from. No, if we put the atoms in any of these three dynamically decoupled states and measure their lifetimes, it's exactly as long as a lifetime was going to be in any individual spin state. And even if you put superpositions in it, it doesn't change. And there are two reasons contributing to that being the fact. So the first one, maybe it's really one reason. The leading reason is in rubidium, the interactions are almost completely spin independent. So if you have symmetric interactions, collisional interactions between the atoms, there isn't a mechanism to change this degree of freedom. And then to the extent that's not zero, the gap between these states is very, very large, so that now we don't have any kind of resonant way to change the state.
I see. Yeah, the gap, you mean the Fouquet gap or the actual gap?
I was meaning the
dress.
So in the dress state picture here, the Fouquet gap is huge here. That's a scale. This picture here, in the rotating wave approximation, if it were the case that the X state was exactly symmetrically placed between the Y and the Z states, and I put atoms in the X state, then binary collisions could conserve energy and put something in the Z state and something in the X state. Those are the same kind of spin changing collisions that have a super small magnetic field. So it's the energy differences here that block any kind of resonant transitions that the spin dependent energy could otherwise do.
I see. Interesting. Okay. You think you can explore like physics of localization with this kind of Hofstadter, this kind of Aubry-Andre system?
Yeah. So when we were writing this paper, one of the, I wouldn't say it was, one of the interesting things we began thinking about is what is the connection of this kind of physics, both to localization and also chaos, in the quantum chaos sense. And what I've come to learn is that the Aubrey-Andre model is a very intermediate model in single particle quantum chaos. So in both the, because it's a dual model, both in the localized and delocalized phases, it's not chaotic, it has completely normal behavior. However, at the critical point, it's a quantum fractal, and it exhibits almost chaotic behavior. So it has what's called semi-Poisson level spacing distribution. So it has avoided levels, but it's not like Wigner-Dyson or anything like that. So it's a very much intermediate model. So it's only at the place where it has fractal behavior that in fact takes place. So I think that there are some neat things to do with localization, and for me, this connection to marginal chaos is also quite interesting.
Okay. Okay. Other question for Ian? Okay, Ian, thanks a lot for this really wonderful talk.
Yeah, thank you.
Very interesting. Yeah, hope to see you again soon.
Yeah, thanks again for having me.
In person. Yeah, great.
Yeah.
Thanks a lot.
Yeah, bye-bye.
Bye.